in this video, we're going to cover just the four basic conic sections that can describe four different types of orbits. And so if you remember, right, our equation, our solved two-body equation resulted in r as a function of nu, which is our true anomaly, is equal to a times 1 minus e squared. Let's double check myself because I always write stuff wrong. All over 1 plus e cosine of nu. So the e is our eccentricity, a is our semi-major axis, nu our true anomaly, and r is the distance from the center of the Earth to our spacecraft. So let's go ahead and start. So our first conic section, and forgive my circle drawing ability, is a circle. Now, a circular orbit has an eccentricity of 0. And being that our eccentricity is 0, and if you remember, eccentricity is how elliptical something is. So Earth here, spacecraft there. That means there is no apoapsis and no periapsis. All points are equidistant from the center of the Earth. And thus, our A is equal to R. So this is R and A. And it's constant for the entire orbit. So yeah, spacecraft R is equal there, as it is to 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 there. It's a circle. So then we'll move on. We'll write circular because you can't really tell that this is a circle due to my amazing artistic abilities. So next is the elliptical orbit. This is the one we started with in the first episode. So this is a very elliptical orbit. So we've got our Earth right here. Let me just draw that as a unique symbol. We've got our periapsis. We've got our apoapsis. We've got, so that's the center line. Half of the major axis is A, so from the center to the periapsis or to the apoapsis. These are the same. And so our elliptical orbit, and then our R is a function of nu. So R nu, and that is equal to our solved two-body equation right there. Then we can actually, so the periapsis is A is equal to A times 1 minus E. The apoapsis is equal to A times 1 plus E. Our eccentricity must be greater than 0, but because if it was 0, then it'd be circular. But it also must be less than 1. So eccentricity can be anywhere from 0.000001 to 0.999999. And as it gets more eccentric, it will look more and more cigar shaped. So we're going to move on to our parabolic orbit. So parabolic orbit. And where I'll draw the Earth. And then we'll draw the orbit. So that's the orbit. And we've got RP, our periapsis. We've got R, which is a function of nu. Let's draw this a little bit better. The parabolic orbit doesn't fully circle the Earth. It just kind of flies by. Now P, if you remember right, P is 90 degrees away, 90 degrees of the true anomaly away from the periapsis. So our conic equation for this is actually R nu equal to P over 1 plus E cosine nu, and P in this case, P is equal to 2 times the radius of the periapsis. And the reason that we use P instead of A is because for a parabolic orbit, the semi-major axis is infinite. And our eccentricity for the parabolic orbit is equal to 1. So this is, this is a flyby of the planet, not truly orbiting it. And then we'll move on to the last of the conic sections, and that is hyperbolic. All right, so hyperbolic looks very similar to parabolic. So we've got Earth, we've got our orbit, got our periapsis, but the biggest difference is the semi-major axis is on the other side, or the center of the orbit is actually on the other side of the Earth. It's kind of a little weird. So as opposed to it being over here, it's over here. So this is our center, and this is our A. So A, our semi-major axis, is actually negative, or less than 0. And our eccentricity for this orbit is greater than 1. And we'll talk more about hyperbolic orbits later when we get to calculating gravity assist and flybys and planetary captures. That's a little ways down the line, though. All right, that about covers it for today. Thanks for watching.